Namaskar. Welcome to our channel, The Consultant's View. Urban drainage system is one of the major challenges in many parts of our country, India, mostly in those topographics having flat terrain. Many reasons are talked about and discussed at length by the experts in different forums. Leaving aside the maintenance part, which I think is the major one of the other reasons can be attributed to limited space of construction of drains of required size, shape, and most importantly, the invert levels, which the system requires from hydraulic point of view for efficient flow of stormwater. There are technical solutions. The experts of drainage specialists do propose the appropriate ones. Often it invites debate at different levels and arguments between engineers and technocrats versus administration and political setup. Right from design consideration of storm event return period, rainfall prediction process, outfall locations, struggling to have land, drainage route finalization, etc. and etc. There are many other factors. Today's technical session focuses on discussing one solution not much talked about in respect to storm water drainage system in specific, which carries only storm runoff in an urban setting. The point which has not been generally discussed it is evaluating the efficiency of storm water drainage system if it is integrated with the water bodies within or adjacent to the city. Let's discuss on this. It is very interesting. Here I take a case study from a city in the central part of India. I was involved in that project as hydraulic modeler. The study was done in 2012-13. It was a feasibility study in a city of lakes having about 155 water bodies or lakes, locally called as talab. All are within the city limit of about 400 square kilometer. Most of them were natural in origin. Gradual deterioration of water quality and water quantity in lakes had been a concern for the civic authorities. Proper management and protection of these water bodies were the needs of that time. Earlier, the authority prepared two separate engineering project schemes, one for storm water drainage and the other on lake protection. However, while preparing those schemes, the underlying benefits integrating lakes into the storm water management system were overlooked. Let's now come on the engineering side. Surveys were done, primary and secondary data were collected, tertiary informations were gathered, the informations and data were reviewed, specifics were compiled, collated and analyzed. Validation based on sampling was done at ground level. A comprehensive drainage network was proposed after catchment delineation, keeping in view of utilizing the existing system as far as possible. Rainfall analysis was done, intensity, frequency, duration, IFD curves corresponding to different flood frequencies or storm return period were generated. Selection of storm return period was done judiciously, keeping a balance between practicability of construction, importance of the area, extent of existing network, nature of the land, sustainability of engineering decision, and overall the capital and operation maintenance cost for providing such an infrastructure component. Primary selection of catchment subbasins was done based on size of lake, location, terrain of catchment and interconnectivity possibility, representativeness. 4 subbasin drainage systems were found to be representative for all types of catchments. A matrix evaluation was done for selection of one specific lake system. It was taken up for subsequent modeling, study and analysis. IPASWIM storm water management model was used as a tool for modeling the storm drainage network for this study, considering its applicability and appropriateness with respect to ground situation, project purpose and of course budget for this study. SWMM, that is SWIM software, was developed by United States Environmental Protection Agency USEPA. SWIM is reported to be capable of accurately estimating the surface runoff due to precipitation. System consideration data such as subcatchment characteristics, system boundary, subcatchment area, land use, water bodies, etc. was given as input to the model, and also basic parameters such as separate system, evaporation and rainfall, infiltration and percolation, geohydrological considerations, geological overview, soil characteristics, groundwater dynamics, lake bed seepage, etc. All these data were given as input. Existing drainage system was studied. This system started from a small subcatchment of the lake system and culminates to its outfall at the canal, which ultimately leads to a river. From the spreadsheet design calculation in Excel, it was noted that about 25% of the drains were undersized with respect to runoff at peak flow. Apparently, the system needs substantial renovation. Proposed drainage network was developed for two conditions. One, without additional integration of lakes. Number two, with additional connections to integrate the lakes. The hydraulic modeling was required to assess the level of stagnation, water stagnation at the different conditions, its extended effect and duration with respect to time, etc. Such analysis justified requirement of integrating lakes into the drainage network that would act as buffer storage reservoirs. Let me discuss the model output in both the conditions. Hydrological simulation time area method of surface runoff and the hydrodynamic simulation of the pipe flows are checked, and the functions of network under dynamic load and operational conditions were checked. The results also incorporated important factors of runoff losses from the system due to evaporation and infiltration. Modeling assumptions were done as appropriate and relevant. Two rainfall durations were selected, one for high intensity and short duration, and the other is annual rainfall over the year. Event A, 30-minute rainfall duration with an intensity of 38 mm per hour. This event was the most intense rainfall as per the rainfall data analysis done, occurring over a short time, and was used to assess primarily the capacity of the system including lakes. Event B, rainfall for an entire year adopted. This event was more directed towards having a yearly water balance of the reservoirs, that is lakes, and as such represents the lowering of water level in the lakes. Weekly average evaporation data for last 5 years was collected, and average evaporation data 5.4 mm per day was arrived at, which was considered all across the simulation for modeling purpose. Hydraulic simulations were done based on three network scenarios. Scenario 1, existing drainage system within the catchment connecting to lake 1 only. Scenario 2, existing drainage system within the subcatchment connecting all lakes in the system. Scenario 3, proposed drainage system within the subcatchment connecting all lakes in the system. It could be inferred from the model run scenarios that with interconnection of lakes to the drainage system, flooding gets reduced. There was a possibility of reducing pipe sizes at the downstream side of the lakes in the network. Even the bed slope of the conduit could be made flatter. This would save the civil works cost. The water balance of the lake system was determined on the basis of data time series. It was seen that the average water volume after a time series of 1 year remains constant. The possible groundwater recharge by storing storm runoff by using lakes was addressed. The lakes were proposed to be developed as community level groundwater harvesting units. The major practical challenge anticipated was accumulation of silt and sediments in the water bodies that would get carried by the surface runoff. This needs maintenance program. In addition, a small stilling basin can be accommodated at the upstream of pond or water bodies as silt arrestor. Even if there is some intrusion of waste in small quantity, maybe from street animals or birds, It can be managed to an extent by providing diversion mechanism at the entry point of the water body. It will restrict wastewater with pollution level not above permissible limit to get entry in the lakes. The main advantages of the proposal and recommendation of the studies are maintain water balance in the lakes, upgrading lakes for recreational purposes, reduce the conduit size, reduce flooding, keeping the provision of taking up water conservation projects, provide much needed buffer storage in the system. Thus, it was evident from the study that water bodies in the drainage system acts as shock absorber of the storm drainage system. I repeat, shock absorber of the system. This concept of integration of water bodies in the drainage system is not new. Maybe there had been some practical problems which has not allowed it to take the preferred seat and rendered a feasible option in general. This video endeavors to re-promote this concept wherever possible exclusively for storm drainage, not for combined system. Believe me, it will drastically improve the storm drainage system efficiency and also support water conservation policy. It will surely contribute to a high level of sustainability with respect to all three pillars: economic, social and environment. Thank you viewers for joining this channel. Namaskar.